Roll 'em. Rolling, rolling, rolling. Little problem in the control room here. David, did you find out about the homeworks in the lounge? The lounge boxes? Did you find out about getting them?
No.
Okay, so we had a little disconnect here. Those who turned in homework into the lounge boxes.
What room is that?
See the problem? It's
It should be 240.
Okay.
okay.
I'll go get them right now.
Yeah, check with the the gal. I'm not sure who has a key for you or something like that, right?
It shouldn't be too difficult.
Yeah, okay. Okay.
All right, I'll be back in a bit.
Okay. Okay. So what's happening on the wait list and stuff like that? I gave the list of the names I called last time. See what's they're doing is, some people who are enrolled are not showing up to class, and so we'll assume that they're not part of the class. But until they actually drop the class, they won't enroll the people on the wait list. Okay. So we're waiting now. As those people drop the class, and people on the wait list will get added in, okay, as it goes along. And there's not much I can do about that. It's a little. I was trying to be organized about that this time. Did my best, but I'm finding new problems. But that's the situation. So I can't say positively because I don't know, but I just don't believe there's going to be a problem for anybody who wants to be in the class. I mean, I just think it's just going to take time for people to drop out as they do. Okay. Any questions or anything? Okay. As I said, I'm going to leave today early. I'm going to leave in about 35 minutes. I've got a plane to catch to Boston. So David is going to give the lecture today and Wednesday. Okay. I'll probably miss a couple more lectures through the term, and we'll have maybe Rob teach one of them or some of the other grad students. So I'll miss a couple more. I just have to do. Yes?
Do you still have office hours Wednesday?
No, thank you. I will not have office hours Wednesday. All right. I'll be in Boston. Why don't you ask him? That'd be good. Yeah, it'd be nice for him. Yeah, I should. That'd be good. I'll try to have some extra ones maybe next when I get back or something like that. I'll try to do that. This week's no trouble. Yeah, ask David. Maybe he can. Or Sorab, maybe Sorab. Okay. Anything else? Any other questions or anything? Cyril? Okay. So let's roll. We did last time was we started the differential pair. I'll take this off. And what I want to do now is do the way that we analyze these differential pairs. So the idea was we took our basic circuit, which is a different. So we're now, instead of having a two-port where we had before, we analyzed it. Our two-port basically like this. There was a V in and a V out. Now what we did is we said, okay, we're going to have a balanced circuit, so we'll have a V1 and a V2 in. Okay, I'm reviewing here now. V1 out and a V2 out. Okay. I said, well, these aren't really convenient variables to use, and I redefined the variables to look like this, and I have a Vn differential over 2 and a minus Vn differential over 2. Okay, and then we tie this to a Vn common. So between these two leads right here, you see Vn differential. Average of these two together, you see Vn common. So this is actually just a different way of, I could just make this look close as I can. So here's V1 in here, and here's V2 in here. So this is two independent sources. These two are coupled, right? This is Vn, this is minus Vn. So there's two independent sources here. So two sources, just a change of variables. And this turns out to be much more convenient. Then we can define the same thing, average value, and voltage between these is V out differential, right? And the average value of these is V out common. And we defined a couple of new gains. V in differential, which is equal to A differential mode, and V out common over V in common, which is a common mode. See, and generally the reason we do this is because the way we do our circuits and the way we want things to operate, we'd like this to be as small as possible. That'd be ideal. And we like this number to be really large. So that actually has a lot more meaning to us than, all the value of V1 in versus V2 out, something like that. We don't have any, ways that we use the circuit that constrain V1 relative to V2 or V1 in, and so on. So this is kind of why we do this. We'll design our circuit such a way that we'll have a smallest possible common mode gain and largest possible differential mode gain. We're probably going to hand out the project on Wednesday, this Wednesday, and it's going to be a differential pair, followed by a gain stage is probably what your circuit will look like. So we'll give you some specs on differential mode gain and common mode gain and things like that to design with. Okay, so that'll be what we shall have to do. Okay, so change of variables, differential mode, common mode gain. Now, how do we analyze? Yes. He's right. Okay, talk really loud.
What was the reason to divide the differential into 2 times 1?
This, well, it's just why having 2 sections, I guess. There's other ways I could draw this equivalent input here. Okay, I could do it like how else could I do it? Well, just think about it. Okay, let's try. If we did it like this, let's say I didn't separate it into 2 parts. Okay, then I could put the common mode gain down here, right? But that's not exactly the same as this, right? Because this voltage right here is V in common, and this one's V in common plus V in differential, right? And so the average value of V in common here, so this would be V in common. The common mode gain isn't exactly V in common if I do that, right? It'll be here. The common mode gain would be, common mode voltage would be VIC plus VID over 2, right? See that? It's not symmetrical. So I need to make it sort of symmetrical so that if I average these 2 voltages together, what do I get? Truly, it's VIC. Okay. If I take the difference of these 2, VI common equals V1 plus V2 over 2.
Why not just put VIC? Split the VID over 2 and negative VID over 2.
Okay, so what's your idea? So let's try it. Try again? So give it to me. I'm open for an idea here. Okay, so.
I'm saying if we average the 2, you just end up with VIC.
Right.
Oh, never mind.
Okay. There are other ways to do this. This is not the only way that you can do it. This is just one that works well. Okay. I can't think of another one right now. That's why if you came up with one, I'd put it down right now because there's probably other ones, and I just can't think of it right this minute. But the important thing is that V in common is the average, and V in differential is the difference. So whatever way you do that to put in some thing, this is okay. All right. Now let's do a circuit. Okay, so let's take the common differential pair that has these characteristics: large value of differential mode gain and small value of common mode gain. There'll be lots of things inside here, but this is the characteristics we like. This also has a characteristic, and let me put a resistor down here. So we generally have a current source. We don't have to have a current source here. We can just put a resistor here. But let me put the current source here for a second. We talked about the large signal characteristics of this thing. Okay, put a long wire there. So let's do small signal now. Let me talk a little more about large signal before I go on. One thing nice about this circuit, this is a gain stage, right? And let's look at our other gain stage that we have so far. Okay, this guy. You know, this one's really difficult to bias, right? You have to get this voltage just right on to get this voltage so it comes out to be, you know, at some, like if this is VDD, typically you'd like to have this at VDD over 2. You got to really set this voltage here very accurately to get this DC voltage to be at the center of the output range. Like as you've seen in your homework, some of you asked me the question today, I guess it was like this inverter stage thing, right? Which problem that was? Yes. This guy, right? Wasn't this one of the homework problems? Right? And it said, okay, bias the input so that the output was equal. Well, you do a little hand calculation, and you try to find out where that works out, and it's very difficult. You need to do, it's almost impossible to do with the hand calculation. It's because the gain's so high at this stage, right? You really have to, if you plot V in versus V out, the thing looks like this, right? So if you miss, you get V in here, just a little bit off from this point where V in equals V out, you make an error. So what you got to do is sweep V in SPICE. Take V in and sweep it, do a DC sweep, so you get this curve. Then you might blow it up and do it again. You know, you find what this voltage is at 1.2 volts or something like that, right? It's somewhere in this range. Then you blow it up again and plot it again, and you get, so, and this is maybe over a 10 millivolt range that you do it. And you can find out this point where the input equals the output, right? So use a DC sweep to find your bias point for these really high gain stages like this, okay? Well, that's really tough to do. I mean, how are you going to do that in a circuit? If this thing needs to be accurate to within a few millivolts, how are you ever going to do that in a real circuit? And you can't, you got everything. The power supply is changing by 10%, the transistors are changing. You're not going to be able to get anything that accurate. So how do you bias anything up? If you're using these kinds of stages, it's a nightmare to bias things up, okay? This is really easy to bias, okay? Why is that? It's because, if we look at the common mode voltage here for a second, this, what will happen is, this voltage can move up and down, and what is it going to be? This voltage right here will be V input common minus VT minus VD sat, which is dependent on what ISS is, you know, VD sat, which is corresponding to ISS over 2, right? Because only half the current goes to each of these sides. So you're not very sensitive to the DC voltage on these gates. This thing just sort of floats around, and it ends up with the current that's set by this current source down here. So you're not, so, you're right, I told you earlier, this is ISS over 2, and this is ISS over 2. So this current now is a function of this current source, not the DC voltage on this gate, and this can change over a fairly good size range. That's what you're going to do in your project. You're going to design to make that range, you know, maximum. Whereas this circuit, boy, you've got to get this voltage exactly right. Or this circuit here as well. See, there's no, so this is setting the circuit parameters by a current, where this is kind of voltage controlled. You want to do things like this where you set the circuit by current, not by voltages. Okay. All right. That's another really good reason why you might want to use a differential player, even if you don't want to do differential amplification, even if you don't really need to have two independent voltages come in. Okay. Or, all right. So let's go back and let's look at this again. And how do we analyze this? So let's do differential mode gain. Okay. And let me put a resistor down here. Not even have a, you know, a differential means I have plus V in differential over 2 on this side, and minus V in differential over 2 on this side. Okay? And assume that VIC, little VIC is equal to 0. Generally, we run between a minus VDD and a plus VDD over 2 and a minus VDD. I forget the 2. Run between plus and minus supplies. Typically, how we'll bias these kinds of circuits up, right? Between plus and minus supplies. Then you can return this stuff to ground, right? And that'll bias this thing up, you know, approximately okay, probably. Okay, so it's purely symmetrical. This transistor equals this transistor. This resistor equals this resistor. Let's do the small signal now. So all these DC supplies become grounds for our small signal analysis. And what's the current flowing through here? Well, it's going to be VID over 2 minus VS. So it's a little delta V, delta VGS on this side that we have. The current here will be delta VGS times G sub M of this transistor. This is exactly the opposite sign. So that means it's going to be a current in this direction of delta VGS times G sub M. This current equals this current. How much current is going down here? This current, so let's do KCL on this node. This current plus this current plus this current, well, this current minus this current has to equal 0, right? Getting the polarities right. If this current delta VGS times G sub M, and this is G sub M times delta VGS, remember, because this opposite polarity, this current coming in, this current leaving, what's this current going to be equal to here? 0. That's 0 current. What's 0 times RSS? 0. All right, okay. The tough questions here. Okay, so that means this voltage never changes. That's a virtual ground. That's what I meant by a virtual ground. By action of the circuit, this voltage never changes. It's a small signal idea. It's not a large signal idea. I mean, this has a DC voltage on it. You know, if this is grounded here, it'll be some minus VT minus VD sat. So it's a DC voltage there. But in terms of the small signal, it's a ground, just like we grounded the minus VDD and plus VDD. Okay, if this is grounded and this is grounded, this half of the circuit is separated from this half of the circuit. See that? There's a ground here, and there's no connection between these two halves of the circuit. This is VOD over 2, and this is minus VOD over 2. So let's just redraw this half of the circuit. So this is a trick. Doing a trick here now, right? It's called half circuit analysis. So this is a ground on this side. This is VID over 2. This is VOD over 2. Here is RD, and here's a ground up here. So what is this gain of this circuit? This is a common source with an RD resistive load. So the ratio of this node right here to this node simply going to be minus GM times RD in parallel with R0. Let's call this transistor 1. Okay? VOD over 2 or VID, I can cancel out the 2's, and that's equal to ADM. It's VOD over VID. So by this trick of noting that this is a virtual ground because of the symmetry, I can break the circuit into two parts. I can analyze, look at one side. It's a circuit problem we've worked before, and it gives us our differential mode gain. Do I see that? So this is half circuit analysis. Only half of the circuits here. I mean, I could do the other side, be minus VID over 2, and I get a minus VOD over 2, and I'd still get the same thing. The minuses cancel, the 2's would cancel, so I get differential mode gain again. So the differential mode gain of this circuit is simply minus GMRD in parallel with R01. If this is transistor 2 here, I mean R01 equals R02, right? So it doesn't matter which side I work with. Everybody see that? Any question about that? Okay, now here's a little trickiness here. What about output resistance? Output resistance is looking into this node right here. Let's call this R out. The current into that node is I out, let's say. I out. So we have VOD over 2 divided by IOD, okay, the differential mode current going into this node right here. This, as you R out, is defined as being the output differential, the voltage output differential part of the voltage on this side, divided by IOD. But you can see what's happened here. We got a little 2 here because only half the voltage is on this side. That's going to seem, so this is going to be equal to 2 times R out. R out over 2. Right? Okay, thanks. Okay? Right. So what is the resistance looking into this node? Resistance looking into this node is going to be equal to, I'm getting fouled up here, let me see how I'm doing. So looking into here, we know that of this half circuit, let's call it R out half circuit, okay, is equal to R01 in parallel with RD, okay? All right, where am I? What's going on here? Oh, I see. I shouldn't do this. Okay, this ratio right here is equal to this right here, equals to R out half circuit. This is the output resistance of this half circuit, and that's equal to R01 in parallel with RD. Okay. And the ratio of the voltage here to the current here is this R01 to R0D. This is R out differential. It's VOD over IOD. You can sort of see from this I get VOD over IOD is equal to 2 times R out of the half circuit, which equals 2 times R01 in parallel with RD. So the differential output resistance of this R is 2 times R01 times RD. Okay, that seems kind of confusing. Let me explain what's going on here. Let's look at, now let's start right here. Here's what I'm doing. We take the output differential signal between these two values. On one side, we only have half of the voltage. Okay? So it's like in your homework problem. So what I'm really doing is I'm putting myself, this is me in the center here, right? Okay, there I am, right? I'm looking this way, I see one half of the half circuit. And I look this way, I see the other half of the half circuit, okay? When I look this way, I see a resistance of R0 in parallel with RD. When I look this way, I see another resistor of R0 in parallel with RD. If I look both ways simultaneously, okay, somehow, I see 2 times R0 in parallel with RD. It's the fact that you're looking both ways into the output of this differential output stage, okay? If you think about our picture back up here, what I'm really looking in, I'm looking into here. I'm looking into both of these simultaneously. So I have an R0 in parallel with RD on this side, and I have an R0 in parallel with RD on this side. So with the two look in series, as far as I'm concerned, right? One R0 in parallel in series with the other one. All right. Okay, so you got that? So that's a little bit of weirdness. So just remember, for a differential, when you take the output differential resistance in a differential pair like this, okay, looking into here, you'll see 2 times the output resistance on one side. The gain, if you look between both sides, is exactly the same as the gain of a half circuit on one side. So here's a question for you. Make sure you understand this now. What happens if I only, let's say I don't look at this side here. I just take the signal off this side. I call this V out. I don't take the differential output. I just take the output off one side. What will my gain be then? Get the question? If I take it between the two, I get a gain of GM times R0 in parallel with RD. I'm saying now, don't take the gain from this side. Take this side relative to ground. What's my gain now? 1/2, exactly. You only get half of the voltage on each side, right? Remember, this is VOD over 2. This is plus VOD over 2. So if I go from here to here, I actually get a positive output, right? Because from here to here is minus. From here, if this is positive, then this is positive on this side, okay? positive, negative, positive, 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 negative, positive, positive. Okay. And I get half. I only get half of the gain. I lose half of the signal because I'm not looking at the signal on this side, which is the other half of my differential signal. Okay, get that? So if you want to go from double-ended, we call this a double-ended. Differential is a double-ended signal to a single-ended signal, which means single-ended only has it's relative to ground. This is sort of definition. So double to single-ended conversion. We have a differential signal to a single-ended signal. You lose a factor of 2 if you use this circuit. Okay, you lose a factor of 2. We'll have another circuit where you don't lose the factor of 2. Yeah.
You're saying the gain is half the regular gain, right?
Half of this gain I just calculated a second ago, right? Exactly right. It's going to be this gain from single-ended gain will be R0 in parallel with RD divided by 2. Okay. Okay, got that? All right. Differential mode gain, we've done it. Now let's do common mode gain. Let's redo this again. Let me put a resistor down here. Common mode gain means we put the same voltage on both sides. So this is common mode. Okay, here's RD, RSS. Okay, now, how can we analyze this? Is this a virtual ground? No, right? We know changing this voltage here changes right along with it, or pretty close to it. If it was a current source down here, this voltage would exactly track this voltage. I don't have a current source here now. I have an RSS. So this voltage can change a little bit, but not a lot. It won't change a lot. It's like a source follower, right? This is VIC, and this is the voltage on the source. So it's kind of like a gain nearly 1. You know, source followers weren't exactly 1. They're a little bit less than 1. So the gain from here to here is just a little bit less than 1. How can we analyze this? Okay, big time trick. Okay, watch it. All right. We take this RSS, and I'm going to replace it with 2 resistors. One here of size 2 RSS, and another one drawn over here of size 2 RSS. So I get rid of that resistor and put 2 resistors in parallel of size 2 RSS, so it's exactly the same circuit. Okay? By that, right? So I removed this one here and just made 2 of them. There's a wire connecting these 2 resistors together here. So here's the trick. Remember, this is fully symmetrical. This resistor is exactly the same on both sides. These transistors are exactly identical, and the voltage is exactly identical on the gates of both of these devices. What direction will the current go through this wire that connects these 2 sides? Will it go to the left, or will it go to the right? No current? Right. Exactly right. I mean, there's no reason you can argue why that current should be one polarity or the other. I mean, this is fully symmetrical. This current will then have to be 0. So even though I have a wire connected here, there's going to carry no current for this purely common mode signal. Okay? If it's differential, it'll be a different story. This is common mode. So for this pure common mode case, no current through here, well, why don't I get rid of it? So I remove that wire. Now look what I have. I have 2 half circuits again, RD, a transistor, and 2 RSS, which is totally decoupled from this trans side, RD, transistor, and 2 RSS. So let's now redraw that. Okay, what is the gain of this? What is it? It's good old common source with degeneration, right? Answer is common mode gain, V out over V in. This is V in IC equals VOC. So it's just directly, there's no 2's in this one. VOC over VIC is equal to, as you all know, I am sure, GM RD over 1 plus GM times 2 RSS. Here's the common mode gain. What's the output resistance? There's no 2's this time, so it's just straightforward. Looking into here, because here's a full VOC on this side, that's the common mode current in there, so ROC is simply going to be equal to RD in parallel with R0. This is half circuit analysis. Basically, you make this argument, you take this source resistor, whatever. Now, this is a current source, this would be infinite, right? RS would be infinite. If RS is infinite, then this gain would be 0. That fits, right? If it's a finite resistance in that source, that tail current source, wherever it is. Now, if you have a finite resistance like this, which this is a true current, an ideal current source doesn't have any output resistance. A real current source does. We'll use a transistor down here sometimes to make this current source. But you can use a resistor. You don't even have to have a current source. Makes the biasing a little more difficult, right? Because then now the biasing is not a function of that current source. It's a function of the voltage across this resistor, which you set by this common mode voltage. Okay? Now notice there's the gain RD in parallel with R0. Yeah, it's GMRD. Looking down, what's the resistance that you see, right? It's R01 with this source degeneration. So that's going to be a fairly large resistance looking down, right? So there's not enough parallel with R0 there. There's something called the common mode rejection ratio, CMRR. It's equal to the common mode gain divided by the differential mode gain. The common mode gain we just said was minus GM RD over 1 plus GM times 2 RSS. The differential mode gain we said is GM RD in parallel with R0. Let's say RD is small compared to R0, just for a second here. If RD is much, much less than R0. And this cancels with this. And this ends up to being 1 over 1 plus GM times 2 RSS. In other words, making that, we can make the differential to common mode gain ratio. I told you I wanted ACM to be very small. I can make it very small by making this RSS very large. How can I make RSS very large? That means I make a really good current, I make a good current source down here. And we'll talk about how to do that into this lecture, next lecture. Okay. So basically, making this larger makes the common mode gain smaller and doesn't affect the differential mode gain. That's the really important point. This is a virtual ground, so I can make this an ideal current source and I still get differential mode gain. As I make this more like an ideal current source, I get smaller and smaller common mode gain. And a specification will be like to have the common mode gain should be like, 1,000 times smaller than the differential mode gain, 60 dB. That's typical. Okay. How would you do that? You would make this resistor, this tail resistor current source, you make the resistor effectively large, right? By putting a better and better current source down there. Okay. So we just whaled through all of this stuff here. Yes.
Could you go back to that slide again for just a sec?
This one here? The CMM one? Okay, question? I'm just taking the ratio. This is the degenerate. This is the degeneration, right? This is the degeneration of the GM that's left here, right? That's what that source resistance does. Degenerates the G sub M.
Excuse me. Why do some books define the common mode ratio as the ratio of the differential mode over the common mode?
Because I don't keep track. I think common mode rejection. I would just, as I did this, which way should I use it today? And so, right, it's common mode rejection. So you think like if you're rejecting something, it should be, I don't know. It could be either way. Maybe it's the other way. I guess the rejection ratio, if it's 1,000, if you reject something, it's 1,000 times. Your choice. I really it's just it's basically the big ratio between differential and common mode, right? And so, yeah, right.
How come you have the RD in parallel with RO on the bottom, but you don't have the RD parallel with RO on the top?
Okay, why is that? Okay, so what is the resistance looking down here? It's going to be RO times, looking down here, with source degeneration, what's the opposite resistance looking into the drain?
Should it be 1 plus GM RS?
GM
RO RS?
2 RSS, right? Right. It's 2 down here too, right?
You have slide 42 of your lecture notes.
No. What is it?
You had it just in terms of RS. I was wondering if that's a typo or not. Should it be 2 RS
No.
instead?
No. It's RS, but RS happens. This is RSS, right? This is equal to RS. It's the source resistance, the value of the source resistor, right? So looking into this drain, it should be 1 plus GM times RS, the source resistor, which for this case is equal to R0 times 1 plus GM times 2 RSS, which is the resistor because of that halving business I do. Okay, so the resistance looking down here is R0 to GM RSS. So that's going to be probably pretty large, right? That's why I threw it out. Looking down here, because of this source degeneration, that resistance is going to be much, much bigger than R0. It'll be bigger by this 2 GM RSS factor. And we'll make RSS big, because we want to make that large so that differential mode gain to common mode gain ratio is large. Okay?
So that's why you didn't have it in parallel with RD?
Yes. It's really RD in parallel with 2 GM RSS R0. So I'm saying that's going to be really big. Okay. Great. One last question, one last comment. Sometimes I did this differential, the single-ended conversion. If I'm not going to take the signal out on this side, I can sometimes just not even put a resistor over there. And that'll save area. It slightly unbalances this stage. So all of our analysis isn't quite exactly right. But let me tell you, it's still pretty close. Okay, so bottom line is, if you are trying to save area, and in your project you'll have area as one of your constraints, if you're not going to take the signal out on this side, you don't need to put a resistor there for it. Now, you probably degrade the common mode to differential rejection ratio a little bit. Well, that's just a design problem for you, right? I mean, you got to trade off. I'm trying to minimize the area, which is cost. If I can do that and reduce that area a little bit and degrade my CMR a little bit, maybe that's a good design thing to do. Okay? So you can go through this, and basically it's the same answer if you just take one side, but like I say, the gain is lost by a factor of 2. Okay. See ya next Monday. Okay, I'm going to be gone. I'll try to answer mail if you got some questions there. And we'll take a little break right here, and David will take over. And okay. But I give it to David, because now I'm the doctor. Yeah, so I told him about this. So you'll get the network. Yeah. Actually, I have none of my home. He added the net list. He added the net list, and I told him, regrade. It's a regrade.
Okay.
What am I?
Okay. All right. When are you back in town? Okay. I'm sorry?
I'll be in Thursday morning.
Okay. Okay.
He's not going to be here on Wednesday.
So can you hold his office on?
Oh, good question. Let me get back to you on that. One of us should be able to. Either me or Sarah. Okay. Sure.
Okay. He's trying to calculate R out for this circuit with source dependent.
Mm-hmm.
So this is a small signal, right?
Mm-hmm.
Okay. So this is IT and this is IS. I just don't understand why is IT equal to IS.
Okay. Let's ignore this resistance.
What do you mean ignore?
Means that
It's infinity.
it means that pretend it's not there.
But it didn't.
Because he's calculating for this only holds if this isn't here.
Right.
Okay. So that's basically, he's calculating this, and then at the end, he does, RG only comes into play afterwards at the very end. So it's basically IS equals IT because he's first calculating this R out prime.
Oh.
So it's just sort of the order of his operation.
Oh, I see.
All right.
Okay. Okay. Basically, when he was talking about this one.
Okay. So common mode
Right.
game analysis.
Oh man, I forgot my question. I can talk.
Okay. Okay.
Will you show up at ourselves Wednesday morning for the home students?
Someone just asked us that. I'm usually not on campus on Wednesdays, so I can't answer for Saurabh. But I guess the answer is yes. We'll make sure that either Saurabh will hold extra office hours Tuesday night, or I'll hold extra office hours Tuesday, or that'll be office hours Wednesday. It didn't occur to me that we'd need to rearrange our schedules to accommodate that. So,
Is something we could check later on in these weeks?
well, we will, put something on the news feed.
Sorry, this is rough.
So he said these circuits were really hard to bias by themselves or something, so that you put them in a differential thing to bias it.
Okay.
And I don't really understand why putting it here would make it easier to bias. He said something about it's not voltage dependent, it's current dependent.
Okay. Here's why. It's basically because let's assume that you just had a standard single transistor amplifier.
Yeah.
Okay.
Right.
Okay. And let's assume that this R and R out were both really high, so the gain is really, really high.
Okay.
Okay. And let's assume that basically you need to get this between 1 volt and 2 volts in order for everything to be set up right. The gain's 1 million. It's not going to be that high. That means your voltage precision here needs to be really, really good. You need to set it to like 1.035725 volts to get everything set up right. Whereas here, the common mode gain of the circuit is going to be low. So your common mode, like where you set, if you set like 1 volt and 1 volt, like the common mode gain is low because typically RSS is high, but you can apply zero differential, and so that you know that you're not going to be tilting your circuit. In other the differential voltage is it's easy to set up a differential voltage of 0. In other words, nominally the bias point is these two voltages being the same.
Okay.
It's easier to set up two voltages that are the same than setting up one voltage that is equal to something else, like 1.035725.
Oh, okay.
Okay.
Wait, so this is not really a negative, it'll be the same voltage as this.
Well, it's 0 and negative 0.
Oh, 0 and negative 0.
They're the same.
And then why does that make it easier to bias here?
Because if these two go up together, like if you were to ask me what voltage do I need to put here to get this in saturation, I'd be like, shit, I have to calculate all the math, right? And it might end up being one point, it might be something that you have to be really precise on, right? But here, you say what voltage do you need to put it in to get it into a reasonable operating configuration? I'd say, just put like 1.5 volts on each one. And so that, because the common mode gain is low. Okay.
Okay, common mode gains.
All right. Let's get started.
Okay. So I'm going to go until 12:30, starting talking about current sources. Before I get into that, one question that was asked by a lot of people were office hours. Professor Broderson isn't going to be here on Wednesday, so everyone wanted to know if we were going to hold office hours in his stead. Probably. We will do something. It is unclear. I mean, we can't get into his office without him, so the office hours will not be there. Unclear as to where we will hold office hours. My schedule will probably not allow me to hold the office hours during his time. I'm usually busy then. I might be able to rearrange my schedule. I can't comment on Saurabh's availability because I'm just not certain what his schedule is like on Wednesday mornings. What I will tell you is that we will figure out a time to have additional office hours before the homework is due, and we will post that before the end of the day on the news group. So also, just this is something that I noticed with the news group pretty recently, is that basically, I think it's that if you post your articles from Google onto the news group, then they can't be read from the internal newsreader, which is typically like you use Outlook Express. I'm accustomed to using the Google newsreader, and we had gotten some comments that like some of the questions on the news group hadn't been answered. What actually had happened, I think, is that Saurabh and I had posted it via the Google News group, and probably some of the students were checking from the internal news group. So just by a show of hands, who tends to use stuff via Google? Okay, who tends to use stuff via the internal news group? Okay, I think that just basically by democracy, since most people are already using the Google News group, rather than forcing everyone to shift over to using the internal newsreader, everyone might just want to transfer over to using the Google newsreader so that they can see everything. It's probably the safest bet. We can't enforce that people have to use the internal newsreader. We can't enforce that anyways. So the people who use the internal newsreader would probably be best served by just using Google. The interface is, as far as I know, really simple, and as far as I can tell, there's no compelling reason to use go through the internal portal as opposed to via Google. If any of you have particularly strong rationales as to why everyone should switch over to the internal newsreader, send email to the TAs, and we will listen to what you have to say, but no guarantee of agreeing with what you have to say. I don't know. There is a delay. Yeah.
I think the biggest reason to use the internal news group would be that everyone can actually read what you post.
Right. But everyone can also.
Only if everyone reads it through Google. If you post to the internal one, both internal and Google people will see what you write. If you post to the Google one, only people in Google will see what you write.
So you guys should post an internal.
Okay.
There's web news. You can
Okay.
connect to the internal.
Okay. So this is a learning process. We will try to put. That's a very good point. Does anyone know about if one is faster posting than the other?
Internal is faster.
Okay. Internal is immediate.
It's all local on one server.
Okay. So yeah, I guess Saurabh and I will then try to use the internal. There's no way that you're going to convince your classmates to do that, and some classmates have been very good about answering the questions before Saurabh or myself get around to checking it. So if we see that someone's answered it, it might be on Google, and so we might not answer it. So you're probably still well served checking Google. We will try to make it a practice. Saurabh and myself will try to make it a practice of replying via the internal news group. Are you certain of that?
Yeah, I track both. I use SST and Google. So,
An executive decision about this issue will be made shortly. Check the news group. Check using both Google and the internal newsreader so that you know what the executive decision is. But you're certain that some of the stuff from the internal newsreader just doesn't show up on Google.
Ever? How long did you wait is the question.
well, some post that is 2 days ago, I switched to my
Okay, that's certainly long enough. All right. All right, let's get back to the material. If you guys have suggestions as to how everyone can be happy using the news group, post it to the news group. CC Saurabh and myself, because I haven't used news groups in around 10 years, so I'm a bit of a novice at it as well. Anyways, getting back to the material at hand, we're going to start talking about current sources. Before I do that, were there any questions about differential pairs? Okay, we will talk more about them in section. It's important to get a handle about this about differential pairs because they're used a lot, very typically, and I think Bob glossed over this. Signals are handled differentially, and there are a lot of reasons to do that. So whether or not you use that differential pair to convert a differential signal into a single-ended signal, or you keep differential signaling throughout your entire chain, which we'll be doing later, differential pairs are used quite extensively. And there are some easier biasing issues. Yeah?
One more is, can you actually use an example for the biasing for the differential?
Okay, so he was asking, it's Phil, right? Rich? No. What's your name again?
Josh.
Okay, sorry. I'm trying to learn you guys' names. I'm not perfect at it. Okay, so the question was asked during break, and I think Professor Broderson mentioned this briefly, that versus, or let's put an RD. That Professor Broderson had mentioned something about it's easier to set up biases for a differential pair than it is for a single-ended amplifier. Am I paraphrasing what he said correctly? Is that what you guys sort of heard him say? And the question is, well, why? VI2, VI1, VO1, VO2. Okay, so these two circuits here, let's assume that everything is set up so that the IDS here is equal to the IDS here is equal to the IDS here. Okay? So ostensibly these two circuits here, here, and here have the same gain, GM times RD parallel ROut. Okay, but in order to set up the circuit on the left appropriately, you need to get this circuit into saturation, right? Which means that this input voltage needs to be set relatively accurately, because let's assume that saturation is only maintained if this output voltage is between 2 volts and 1 volt. Okay, and these are just rough numbers. I mean, there's nothing super precise about these numbers. And let's also assume that GM times RD is something big, like 100. Okay? That means that your input, in order for everything to be set up correctly, has to have approximately a 10 millivolt precision. Okay? So that means like your valid input range to keep everything happy might be between, say, 900 millivolts and 910 millivolts. That's your valid input operating range. Okay? So that means you somehow need to come up with this DC bias point of 900 millivolts. And if you have a battery at your disposal, which you do in SPICE, that's great, but you also kind of need to tweak things around to make sure, because it's not always super easy to figure out what that V-in is, especially when you use more complicated circuit models. Okay? Now let's look over here. So as Professor Broderson had mentioned, this thing has a differential gain, a DM, of GM times RD parallel R out. But the common mode gain is much smaller. So if this is an ideal current source down here, can anyone tell me what the common mode gain of this circuit on the right is? 0, exactly. Because no matter what, if these two voltages are equal, VI1 and VI2 are equal, and you move them up and down, if we call this ISS, IDS of this guy is always equal to ISS over 2, likewise with this. So that means you've always got the same current flowing here. So in order to get this circuit operating happily, all we need to do is guarantee that VID is equal to 0, which in general is easier to do both in terms of real circuits and in terms of figuring out the math in your head, right? And that VIC probably has a pretty big operating range. It might be on the order of like 300 millivolts or like a volt. And again, these are ballpark numbers. But in terms of setting up your circuit in SPICE or hand analysis, or actually for real if you were building a chip, it's far easier to get the biasing on a differential pair correct as opposed to just a single-ended amplifier. Okay, so that's the basic motivation as to why Bob said what he said. Is that clear to everyone? Great. Okay. Current sources. So for lots of reasons, we want this. We want a current source that has an infinite output resistance. Okay? So that means that no matter what, if this is VA and this is VB, let's call this I out. I out is constant, independent of VA minus VB. Okay, it's actually independent of both VA and VB, but when you look at two-terminal devices, you kind of have to look at it in terms of the differential voltage across it. Okay, so in actuality, what we get is we get something that looks more like this, where we have this we have this DC current source, but we also have a small signal resistance in parallel with it, which means that as VA minus VB changes, the current through this two-terminal device also changes, right? We've already seen this come up before. We've seen this come up before in the small signal model of our MOS transistor, which has, a plus a VGS. You've got your GM VGS, and then you've got your R out here. And we've already determined, this is on the, there we go. We've already determined that the presence of this R out limits our voltage gain, right? Because the gain for this circuit is always like, when we have it in a simple common source, is always GM, when we have something like this, times R out parallel RD. Even if RD is very, very, very large, we're still limited, our gain is still limited to GMR out. And for reasons that will become clear later, and probably were discussed in like 105, it's nice to have amplifiers that have very high gain. So this small signal resistance is effectively a parasitic element. It limits the performance of your circuit, so hence we want to do whatever we can to minimize the effect of that parasitic resistance. We want to get ideal current sources. Okay? So let me jump over to slide 1A, and this is just basically illustrating what I had said before, that with an ideal current source, the current is totally independent of the voltage, but with a real current source, the current has some voltage dependence that's inversely proportional to this resistance. Pretty straightforward. Any questions on that? Good. Okay. So this circuit down here, on the bottom half of the page, is something that's called a current, that's labeled simple source, is something that's called a current mirror. Because, basically, when you look at this, we know that M1 is in saturation, right? How, can anyone offer why we know M1 is in saturation? Exactly. Because it's because this transistor is diode connected, VGS equals VDS. The condition for saturation is that VDS is greater than VGS minus VT, and because in all the transistors that we've discussed thus far, the VT of an NMOS device is greater than 0, this device is by definition in saturation, unless, of course, there's no current flowing through it. But if no current were flowing through it, then this voltage would have to be less than VT, which means that there's a voltage across this resistance, which means that there has to be a current through that resistance, which means that, well, this thing has to turn on in order to source that current. So this guy's in saturation. So that means this gate voltage is high enough to support whatever I ref ends up equaling. Okay? So now let's look at M2. Okay, M2 has the same VGS as M1, right? VGS2 is equal to VGS1. Okay? So let's assume that we bias the circuit, the output node of M2 high enough such that this M2 is also in saturation. So V out is greater than or equal to VGS2 minus VT. Then this device is also in saturation. So therefore, we can calculate IM2. IDS2 is equal to 1/2 K prime omega L VGS2 minus VT squared times 1 plus lambda V, what we call V out. All right? What we'll notice, however, is that VGS2 equals VGS1. So therefore, and 1/2 K prime omega over L VGS1 minus VT approximately equals IDS1, right? Ignoring this the lambda modulation of this guy. So basically, what you can see is that I out ends up being pretty close to I ref. So you have what's called a current mirror. It takes the current that's in and mirrors it around. Okay? Everyone follow that? No. Okay. Let's try this once more. So let's assume, rather than having this R ref here, I'll redraw it. I've already got the presence of a perfect current source. I went into my lab and gave you this box. It's a perfect current source, and we're calling it IB. M1, M2, and this is just connected. This is V out, right? Ground. Okay. And W over L1 and W over L2, let's assume that the two devices are equally sized. Okay? We can calculate what VGS1 is equal to, right? VGS1, let's for the time being assume lambda equals 0. Okay? That is an approximation, but it's just to keep things simple for the time being. So IDS1 is equal to 1/2 K prime omega over L 1 VGS1 minus VT squared, which means VGS1 is equal to VT plus 2 IDS over K prime W over L. IDS1 is IB. Okay? So we can exactly figure out what VGS1 is equal to. Okay? So now, that's the same VGS that's applied to M2. So IDS2 is equal to 1/2 K prime omega over L 2 VGS2, which is equal to VGS1, minus VT squared, right? And if WL2 equals WL1, the expression for IDS2 happens to exactly equal the expression for IDS1. So provided these two devices are in saturation, then what you can see is that IDS1 is equal to IDS2, okay? Assuming lambda is equal to 0, which is an approximation, or more properly, and both of these are equal to IB. IDS2, if these two devices are not sized similarly, is equal to W over L2 divided by W over L1 times IDS1, which is IB. So basically what we're doing is we're mirroring this current around. The current that comes in is equal to the current that comes out. Yeah?
Wait, so what happens if you include the channel effect?
Yes, exactly. Good question. So, if you include the channel effect, realistically what happens is that both of these devices now have an R0 associated with them. Okay? So VGS1 is a little, this is M1, this is M2, is a little bit more complicated to calculate, but here's a question for you. Let's assume that we had a perfect amplifier, a perfect buffer, that took the voltage on the drain of device 1 and applied that voltage to the drain of device 2. Then you'd see that the two device currents would be exactly equal, right? And we know that the device current here has to be exactly IB, because there's nowhere else for it to go. So basically, what you can see is that what you have is this device here, the output device, will basically equal IB prime. It'll be off by a little bit because of the presence of this guy, which changes the voltage exactly. And it will also have an R0. So this node here is tied to ground. This node is your output node. So provided that the voltage bias on this output device keeps this device in saturation, then you'll have a current mirror whose current mirroring ratio is not exactly defined. It's pretty close, but the issue is that this R0 kind of mucks it up a bit, and then it's also got an output impedance in parallel with it, which will again, depending on your output biasing, muck up the exact current ratioing across the mirror. Okay? Does that make sense to everybody? Yeah.
In your setup, it looks like you put an R0 in parallel with the device.
Yes.
Then why would IB be?
Okay, that R0 is part of the device. I'm just drawing it explicitly. Okay, so the current that flows through R0 is part of the device current. It's just not part of the current that's flowing through the transconductive device. Okay. So that's that. Going on to slide 2. So another way, and I think that what Professor Broderson is trying to convey here is that if you want to set up an output current, of a specific size, one way to do it is basically through this method here. And another way to do it is by setting up a V bias on this node. And so then we know that V bias is equal to VDD times R2 over R1 plus R2. And then you can plug this in here to get your IDS. The issue with this approach is that the VT of a device will kind of change in real life. It won't be exactly what you expect it to be. It'll vary a little bit just due to process variation. They can't produce identical devices every time in the fab. So because of this VT variation, you can have some current output variation. The way to sort of minimize the effect of that is if you make V bias much, much larger than VT, then the proportionality of this effect is somewhat minimized because basically VT is changing by a fixed amount. So, okay. So looking at this device, this transistor is connected in a fashion that's typically referred to as a diode-connected transistor. The gate is connected to the drain of the device. And we saw that right here. Okay? And this is used quite frequently, typically because a current is fed in here, and then it creates a voltage bias that can be mirrored to another device. But what he's trying to show here is that what the current looks like as a function of the voltage, and how this is a little different from a bipolar device. A bipolar device, you might recall, if this is a bipolar device, a bipolar diode, or a true diode, I is equal to I naught times an exponential of, let's call this basically V diode over VT, where VT is the thermal voltage of KT over Q, which is roughly 26 millivolts. Okay, so the bipolar diode has an exponential dependency of current on voltage, whereas a transistor, because it's square law, basically, in this case, ID is equal to 1/2 K prime omega over L VD minus V threshold squared. So you have this is a quadratic, and he mentions that here. So basically, as long as VDS is greater than VGS minus VT, which is always held, right? So one of the conditions for saturation is always held. The other condition is that VGS greater than VT, and in this case, VGS is equal to VD. So once VD is greater than VT, the transistor will always be in saturation. And that's the point that I was making in a previous slide. Okay? So let's look at what we have here. So this is actually the mathematics behind what I was discussing before of M1 M2 V out, and to keep the mathematics simple, you'll notice that he's assuming lambda equal to 0. So basically, you can calculate IDS, as I did before, and then IDS1 and then IDS2. And so if W1, W of L1 equals W of L2, because the VGS of these devices are identical by construction, IDS1 equals IDS2, and that's your current mirror again. All right. So let's actually work through a calculation, which is what he starts doing in the next slide here, slide 5. So with this current mirror, what we have is VDD, RF, M1 and M2 are designed identically, so they're identically sized, and both devices are in saturation. let's figure out how much current flows here, and hence how much current flows here. Okay? So IDS1 is equal to the current through the reference, which is IREF. Well, rather than rewriting stuff, we'll just use his slide. So IDS1 with this plot here, let's get it all on the slide, is equal to has to be equal to the reference current by KCL at this node, and the reference current is VDD minus the voltage here is just VGS1 because the source is tied to ground over RF. So that's just basically delta V over R. We also know that VGS1 is equal to VT times, this is meant to look like a giant square root, and this is an expression for VD sat. Basically, VGS1 equals VT plus VD sat, which he sort of expresses here. So then, you can plug in into here. You can plug into this expression. And so basically, you can solve either for VGS or directly for IREF. It ends up being a nasty quadratic equation, which Bob suggests solving iteratively. You can see here that basically IREF is equal to VDD minus VT times the square root of IREF times some constant. So you can expand out the quadratic equation to get the solution. So basically, if you're trying to, actually, you know what? It's 12:30 on the nose, so we will go through some of this again on Wednesday.
Right.
Which is basically, that ratio is basically